So welcome everybody to the BGD colloquium. It's a great pleasure to have Jacopo De Nardis here. You can tell us about generalized hydrodynamics and anomalous spin transport and spin chains, but let me briefly first request to them to introduce.
So, and very quickly introduce Jacopo. So, Jacopo is an assistant professor in a place called Cergy-Paris, suburb of Paris. Jacopo did his undergraduate in École Normale Supérieure in Italy, the very ENF in Italy outside France. And then he did his PhD in Amsterdam, and then he was a postdoc at École Normale Supérieure Paris and in Belgium. I met, so we both were postdoc together in ENS, but I met Jacopo in a summer school. And that summer school was called Begro Summer School. And the summer school is something very interesting. It's held in a sailing school, in the French National Sailing School. And first half of the day you learn physics, and second half of the day you go and learn sailing, catamaran, windsurfing. But this is exclusively only for catamaran. It's a good incentive to do that. Afterwards, Jacopo came back to Paris and became professor at Cergy-Paris. He has recently done some very interesting work. He actually started during his postdoc on generalized hydrodynamics. And in fact, recently I heard Joel Moore talk about some very intriguing observations of diffusive scaling in a spin chain. And those were mostly numerical observations. And I believe Jacopo has a much better understanding nowadays about where does the scaling emerge. So that's what he's.
Thank you, Trivit, and indeed, thanks a lot for having me here. It's really great. This place is beautiful. I only saw, a few years ago, I was in ICTS in Bangalore, which is also amazing. But this one, I would say win because it's also in the city. But it's not locked in the middle of nowhere. But anyway, great to be here. And yes, I don't know. So Joel gave a talk not long time ago? Or?
Not here. He gave it in ICTS.
Okay. Mhm.
Yes.
Okay, thanks. Okay, so let's start from. Okay, let's start from. Okay, but this is great because now more people are coming. Okay, so starting from very far away, one thing that always fascinates me on in physics is really the fact that you can have a very complicated system like many interacting particles, molecules, or whatever you want. And of course, the law of motion are very complicated, non-linear, but there exists some kind of emergent macroscopic law that describes, for example, relaxation of initial bump of density. And this is the celebrated fixed law of diffusion, for example. And the amazing thing is that all the macroscopic dependence on the type of interaction that you have in a system actually goes in a single parameter, which you can think as a thermodynamic non-equilibrium parameter, which is the diffusion constant, right? And this is, of course, you may say that this is just classical physics, but you can do the same nowadays for a quantum system. You can initialize a system in an initial state and let it evolve. And this is what our friends experimentalists can do. And then you say, okay, but what's nice to do this with classical physics? But in this case, then the whole state is a pure state, so it doesn't have any entropy, not like a classical state. But if you look at the subpart of the system, then this subpart gets so entangled with the rest of the system by time evolution. And this entanglement is characterized, for example, by what people call entanglement entropy, which is tells you like how many bits of A are entangled with the rest. And this typically is proportional to the volume of A. It's called volume law. And now you see that this entanglement entropy basically plays the role of a thermodynamic entropy. So now, if you just look at A, the state looks like a classic. I mean, it has a lot of classical features. It has fluctuations that can be described with classical tools, like, for example, hydrodynamics. And this physically means that if you look at the observable in A, at late time they may relax with power laws, and that shows the emergence of some hydrodynamics. Okay.
This is true for typical state, like going somewhere. It cannot be true for states which are at very low temperatures or very close to ground state, that you get something which is just like classical physics.
It is true. I mean, you always expect that we are thinking in terms of quantum effects. What are the quantum effects? Well, the quantum effects can come also from extra fluctuation that you can get that you may not get from classical hydrodynamics, but also from the values of the coefficient of the transport coefficient. This can be highly influenced by your macroscopic quantum, exactly like the diffusion constant in the classical sense. But yeah, you're right, it's a good observation. But typically when you have a non-equilibrium in low dimension, you go to either
typically go to large temperature.
Yes.
That's
if you wanted to systematically correct this equation in some parameter, presumably length scale variation, right?
Yes.
Can you do it?
Yeah, I mean, I'm just a slide one, so this is meant to be qualitative. You mean in this equation? Which equation?
The first one.
The first one. Yes, the first one in a classical physics, you know that it's valid. I mean, if it's correct, it's valid on I mean, of course, yeah, I wrote it for one dimension, but it's valid on a diffuse scale, right? It's only valid that when if you scale space and time in a way that space is square root of time. That is the scale where you should look. And there is in hydrodynamics, there is always a definition of scales That's usually a set by time. As time goes larger, we expect the scales increase, but how it depends on this type of dynamic.
Maybe I can clarify. Of course, you can write correction terms to the equation.
Yes.
But as we mentioned, structure of this function will at some point break down because there are fluctuations having to do with the fact that your number of degrees of freedom in the box finite.
Yes, yes.
So can you first kind of correction clearly you can take into account by correcting the equation. How do you do the second one?
Yeah, exactly. No one really knows, right? I mean, this is the question of hydrodynamic expansion, if the period converge or not. There's a lot of work by in a field theory. They're very interesting questions, but I will not go to this. We can discuss. Okay, this is just to say that basically experimental experiments can actually do that. But let me say what do I mean by hydrodynamic? But hydrodynamics is simply that I decide that I'm looking at the moment at Hamiltonian evolution. Hamiltonian evolution can preserve some conserved quantity, and I want conserved quantity that are extensive, namely that can be written as sum of local operators. So this has to be a local or a quasi-local operator, okay? And I call this charge density. And the whole point, I mean, to me, it's hydrodynamic for dummies, but for me, it's really the fact that you have a complicated, exponentially complex state, but you want to that is time evolving, and you want to represent it only in terms of a lower amount of information. And what is this amount of information? Is basically the expectation value at position x of this charge density. Okay, and of course, what is this? I will not write. Maybe I will discuss on Thursday if there's time. But that's a bit this huge reduction of information. Now you go from exponential amount to few, or in the worst case, as I will discuss, something that is still infinite but much less complex than this.
So, if we wanted an exact analysis, should we treat rho squared, rho cubed, and so on as independent variables?
Rho, what is rho? Rho. Yes, rho squared.
If we wanted something that will work.
So in this term, you're thinking like taking like powers of these conserved quantities.
Yeah, classically, the square of the quantity is the square.
Yes.
With fluctuations that will no longer be true. So is the framework for the exact formulation of this equation treating all these things as independent quantities?
No, I mean this is a bit. It's a bit. I mean, it depends what you want to do. I mean, if you want to represent states, no. I mean, you should only look at the set of conserved densities which you can, for example, characterize stationary states. Then that should be the case. If you look in terms of operator, then it's a bit different. But I feel like you asked this question because you want to know the certain answer.
I want to know the truth.
Okay, let me proceed because I understand where you want to go, but I think this is a bit too much. I will be very simple now. I will discuss about a classical system, which is very simple, and especially in one dimension, and it's called the Hadrod's model or billiard balls. It's a toy model for hydrodynamics. It's been worked out by many mathematicians, including Albert Spohn and Leibowitz, because indeed it presents. It's a very simple model where we can mathematicians can show rigorously the emergence of large scale of hydrodynamics. So what is the model? The model is simply like particles that move with a given velocity, and you can put it in a standard potential, but in general the interparticle potential is just the typical hardcore repulsion. So if particles are not at the distance larger than their size d, they don't see anything. As the distance becomes less than d, where d is the radius of the particle, it's just infinity. So what does it mean? It means that the two particles coming in, they scatter, they just change their velocity. That's it. They change their velocity at a distance d. Okay. So what this actually mean? I forgot to put the two velocities. So imagine that this is velocity theta and theta prime. So you get theta here. And here you get theta prime, and here you get theta. Okay, so if you follow the dynamic of a rod, you will see something like this, right? But you can choose instead to follow the dynamics of a dual particle, which is actually what defines the quasi-particle of the system, which is the particle that keeps the same velocity. Okay? If you follow the particle that keeps the same velocity, basically what you see is that this particle goes here, has a jump, and then continue. Now, in this plot, you are plotting exactly the dynamic of this. It's what we call tracer velocity. And if you follow this dynamics, basically you see that it has many jumps, and these jumps can actually change the velocity. A large scale, the velocity is not anymore the one that we had initially, but it has been renormalized by the interaction with the other particles. So it's exactly this, and this is called effective velocity. And this is actually a known concept in the kinetic theory. You can find it also in Landau. But Landau did not write actually how to compute this effective velocity. For this model, you can do it. It's an exercise, I think, even a nice exercise for StatMech course. You simply have to add to the effective velocity all the jumps that it does whenever you meet other particle. And here, what you put is just the probability of jumping left if you have a particle that comes. So you jump right if you have a particle that you meet like this, or you jump left if you have a particle that hits you from the back. Okay, and that's it. And it's a very compact formula. It's an integral formula, but you can solve it very simple. And for this model, it's very simple. You can even define a diffusion constant for this particle, because as you see, there is an average velocity, but there is also a broadening around this average velocity, because it's scattering at random. Scattering at random, so it defines a random process around the average velocity, which means that there is an effective diffusion constant for this tracer in the model.
The randomness is coming because your initial state is random?
Yes, the randomness comes from the initial state.
The evolution is fully deterministic.
Yes. The randomness done in the initial state. And basically, you can show that now your hydrodynamic fields becomes, we can imagine that you divide the system into blocks of like your fluid cells, and each fluid cell you put a lot of these rods. Okay, now and you have a distribution of the velocity at each position x and t. You have a distribution of velocity for these rods, and this distribution now it's a function of in theta. Theta is the velocity at each position, space, and time. Okay, and it has a convective flow, and the convective flow actually this is the formula that you find in Landau. Convective flow is exactly what you should expect from the flow of particles. It's just velocity times density, but this velocity is the effective velocity that depends on rho, so it is no linear current. And of course, there is also the diffusive part, the dissipative part, due to the fact that there is indeed spreading in the system. There is diffusive spreading. And this is exactly the reason why it was called atomic model for hydrodynamics, because I mean you can really see this kind of Navier-Stokes dynamic equation in one dimension for a field that now is not just you don't just have like a few hydrodynamic fields as typically you have, like density, energy, and momentum, but you have a continuum of fields. For each theta, you have a field in space and time. Okay, but still it's a valid hydrodynamic
equation. Where does the Course-Gradient scale go?
The Course-Gradient comes from the fact that now you are saying that in the fluid, you are dividing your system into fluid cells, and in each of these fluid cells you have enough particles that you can look at the distribution of velocities, and not just at the discrete.
So the time that you define is also rescaled with that Course-Gradient scale?
Yes, you have to think like that. And you have to think that this description is valid only on a certain scale, as our colleague is telling us. Indeed, very exactly. So this description will be valid only after a certain time, if it's valid at all. And now, what is the whole point? Why I'm talking about this is because there is a lot of models in 1+1 dimension, quantum or classicals, that have exactly the same scattering structure. So the Hadron's model, they are really small, they scatter and they just jump by a distance d. This jump size is fixed by d. But there are a lot of actually quantum model where the jump can be even for a quantum model, you can define a scattering shift or a scattering phase for a particle system, which is in general it's a function of the two incoming velocity. It can be a generic function, and indeed it will be a generic function. But the type of scattering is still the same. It's still reducible to two-body scattering, which is remarkable because in general you could have like a higher body scattering, but all the higher body scattering are still reducible to two-body scattering. And you can think, and this the scattering shift that you have, if for this like imagine to be quantum particles or quantum wave packets, you can always read it as some delay in or advancement in the phase of your wave. So on a large scale, you can always see this as a classical phenomenon of wave packets jumping, scattering, and jumping by a certain distance theta apart. One of these models is, for example, this model for interacting boson, Lieb-Lininger, which is important for experimental realization. But all these models are called integrable. Okay, all these models where the scattering takes its form called the integrable. And now it's obvious to understand that if I know that if there exists an hydrodynamic in terms of this distribution of velocity for the hadrods, there will be also an hydrodynamic for also this quasi-particle of for this integral. And this is indeed what is called generalized hydrodynamics, what we developed a few years ago. And it takes exactly the form as the wrote for the hadrod gas. Here, I'm just writing it a bit more generically, but okay, we will not need a lot of these terms. But the point is always that your fluid is made by a set of quasi-particles, okay, which you can ascertain from effective bare velocity, this parameter theta, which move in this fluid, but in this moving, they actually get renormalized by the local density. So there is a flow in space given by effective velocity times rho. There can be also flow in momentum given by an effective acceleration. This is typically if you have external forces, so your particle can accelerate. And there are also dissipation and diffusion in all directions. So this becomes actually an interesting, even if we are studying 1+1 particles in 1+1 dimension. Effectively, we have a two-dimensional fluid describing the density of velocity of our quasi-particle. Of course, and also no big surprise because quasi-particle are characterized by position but also momentum. So you have one direction is the momentum, or if you want the velocity, one direction is the space. And you get a nice continuity equation for such a density in these two directions. Okay.
One thing, so in the very first model of hadrods, when you broke down the hydrodynamics, where did the integrability structure go? So one, you see that the velocity of the quasi-particle is the same as the diffusion constant.
The integrability simply comes from the fact that you need if you prepare your system if you prepare your rods with the given velocities, after some time they will keep the same velocities. They will have moved all around, but the set of velocities is conserved. Here is the same. The set of velocities is also conserved if you don't have external forces, actually. So in this case, you have no dynamics in the momentum space, but you can actually introduce external forces, and then you can drive the momentum of this particle. But that's just if you are interested in putting system in confined potential and so on. Otherwise, no. The integrability is really defined by the fact that initial set of velocity after scattering, internal scattering, do not change the initial set of velocity. That's it.
You go back to the previous slide. So,
previous.
Yeah. So in the limit of the C, the constant C that multiplies the delta, going to be large values.
Yeah.
That becomes a Beton gap.
Yes, it becomes gap.
And so then the one particle distribution of that is same as the TIFR matrix.
Yeah.
So that's the simplest example of the integral.
Yeah, and in a sense, in this limit, you will recover this hadrod model because you can show that if you do this mapping, you at large C, you can see basically this hydrodynamics, this generalized hydrodynamics as an hydrodynamic for hard rods with the D equal to 1/C. So it becomes exactly like this.
So this limit of C going to infinity is the point infinitely.
Then you become exactly free, exactly. Because
So this fact that you have the same set of velocities before and after stepping is a very 1D phenomenon, right? Because you just exchange.
it is true. It's not just 1D, it's also 1D plus integrability.
Yeah, okay. But if you took that, you're saying, okay, I have a theta, it looks like a 2D model. It's not really a 2D model, because in a 2D scattering, I cannot have momentum, which is transferred, and the set of velocities will not remain the same.
I agree. But what I'm doing here, I'm actually considering full generality 1D with weakly broken integrability. So in a sense, I'm taking a model which internally scattering doesn't change velocity. So it does just give a flux in X. But I'm also putting generic external forces. This could be like a kind of potential or integrability breaking. So this would give the direction of the electric space.
In a sense, should we think of these two dimensions as space?
It's a phase space, exactly. It's like what people call Wigner function. I mean, in a sense, what people call perfect. Yes, exactly. But okay, I mean, this is maybe a bit technical. I mean, like many hydrodynamics, there is always a mapping to what are called normal modes. So if you write hydrodynamic equations, you can always, for a given set of hydrodynamic modes, again, for example, energy, momentum, or pressure, or that, you can always rotate your hydrodynamic mode to a basis where each of these modes acquire a given velocity. So the normal modes are the modes that spread with a given velocity in your hydrodynamic. And indeed, you see that if there is a specific rotation method, which I'm not going to write, where basically the normal modes are called fillings, and now the evolution of the fillings is as the velocity outside. So you have velocity times the nabla of the filling. This basically says that now if you split everything up here, this would just say that it's just like a plane wave propagation for the fillings, which is not the case for the vector. But okay, that's just technical details. What I want to say is that this density rho theta xt actually is not just a theoretical dream, but it can be observed in experiment. And this was done in the group of David White in US. Because basically, as I said, the Liebling model, for example, it has experimental realization is just, for example, a rubidium cold atoms in an optical trap. Okay, so they can trap it to be cigar shape. So then the relevant dimension becomes the one dimension, and you can actually make many of these cigar shapes because they start from a 3D cloud and then they cut it into different cigar shapes. That's the experimentalist stuff. But the point is that now you have a Gato bosons, which in principle you don't know how to read this rho theta x, because this is not just the momentum distribution. It's the momentum distribution of the quasi-particles, which is not a physical observable, but it becomes observable if you actually reduce the density of this gas. Because if you reduce the density in one dimension, actually, effectively, you fermionize the system. You go to the limit of large coupling, and then this rho theta becomes the momentum distribution function of the bosons, or the value of the particle. So what they do, they just expand the trap, and then measure the momentum distribution function. And with this, they can then reconstruct exactly this function of rho theta. Okay, and here there is a rho theta compared with the evolution given by the equation that I just showed you, and display very good again. Yeah, so that's quite a remarkable result of the.
So the diffusion constant that you had in your second term, right?
Yeah.
In the equation. Do you know their profile? Or
Yes. You can. Yeah. You actually can compute them exactly. Yes.
So using a local the experiment is a trap, right? So your profile is not uniform.
Yes.
You are going to use the local density.
Yes. I mean, yes, but it's exact in this case, right? Because yes, you are completely right. The way you compute this is that you compute it in a given reference state defined by a distribution of rho theta. Yes. And then you plug it here in the evolution. Yes, exactly.
So in the case where there are no external forces, where the system is completely integrable, do your coefficients depend on the initial velocity distribution?
Yes. It depends on the velocity. All these coefficients depend on the local states. Depends on the, because they get renormalized non-trivially by the local state. So exactly this. So each fluid cell will have a rho theta. This depends, it's a nonlinear function of the rho theta position x and b. The same for the diffusion constant.
No, I meant you start, let's say you've got your state, you start with some initial distribution of particles.
Yes.
Now that initial distribution need not be thermal or anything. We could start with anything, right? Do these coefficients depend on that initial?
Yes, it depends on that at any time. So they also depends on that at a time. I mean, not sure what you mean. I mean, yes, there will be dependence on the initial condition, but the point that these coefficients do not just depend only on the initial value. They depend also on the evolved value.
You're saying it depends only on the velocity at that location at that time.
No, only at the location, but not at the time of time evolution.
Not at the time of the time evolution. Sorry.
Yes, at the time.
The local velocity and local density at that position at that time.
At that x at the t. Yes.
Yes, but not on what initial state you start.
No, exactly. No. I mean, yeah. It will if you're thinking in terms of like a small modulation, and then yes, you can assume that you only consider the initial state.
So the initial distribution could be very far from thermal, but locally it will start.
Locally we look at why would we have to look at them? No.
I'm trying to understand why things depend only on the average velocity rather than the distribution.
Yes, that's good. You're right. That is true only if you look at certain hydrodynamic coefficients. The flow, this will give you the flow. The flow only depends on the average velocity. Very good. The spreading around the flow, it depends on the fluctuation around the flow. If I would keep going in this hydrodynamic expansion, I will need more and more information about what happened in the local fluid cell. Completely right. But the average flow depends only on the average flow velocity. So,
because you get local thermalization, irrespective of what the initial.
You can think it as a local thermalization. Yes, you're right.
Why is your dynamics completely Markovian in this case? It can depend on the local distribution, but it's completely Markovian, right? I know the distribution now. I know the equation of motion. So you think there are no memory kernels or anything? And normally, if I give you a system like this, I would expect a lot of memories because of integrability, things remember where they
Yeah, that's good. That's a very good observation. In those cases, you have these terms to be infinity. And yes, those are the diffusion constants can diverge, and this signal the breakdown of Markonian, and that's exactly where okay, good. I now leave the full hydrodynamic description to focus on something a bit more simple, but which I still want to use hydrodynamics to understand correlation function. Let me linear response. Linear response is nothing else than doing hydrodynamics. But doing like instead of doing big waves, you just do a small perturbation around the given reference state, and you want to see how this perturbation evolves. But it's completely in the framework of hydrodynamics. So, for example, you can be interested in a dynamic structure pattern of a certain operator, like a spin Z operator in a spin chain. With this plot, what does it tell you? It tells you that the way how correlation spreads in time space, it tells you what type of transport you have in the system. So this is x and this is time. If you have a light cone, a very light cone, this typically means that the correlation they are spread ballistically. If you have a curve of P, you have a diffusive spreading, and something in between diffusion and ballistics is actually super diffusion. Now, super diffusion what mean? What does it mean? It means that actually the diffusion constant is infinity. How do I relate the spreading of correlation to the diffusion constant? This is, if you want, it's the equivalent of Einstein's formula that relates basically viscosity to the response function in the system. You can the integral of this correlation function is given the leading term. There can be a t squared. I mean, the integral of the spreading of this correlation function. The first term can be a t square. The t square is if you have a ballistic transport, right? And this coefficient is typically called root weight, but that's unimportant. Typically this is 0 in a typical system, which doesn't admit ballistic transport. But but you have a t growth coming from this square root of t, and this coefficient is indeed the diffusion constant times the susceptibility. So the DC, what's called DC matrix. DC matrix also can be obtained by Kubo formula by integrating current correlation. So there is this duality exactly like in Einstein formula. You can either see it as a spreading correlation or as the response of the velocity, or the decay in time of the velocity. Good. Okay. So now you see that if you would have something like this, like t to the 2/3, this would be 0, but this would be infinity. So that would be infinite diffusion. And that's exactly, so there is this model, which is the Heisenberg spin chain or XLC spin chain, which is a model introduced in the 30s, but still incredibly displayed some feature that's up to a few years ago, no one knew. Especially if we look at the spin transport at finite temperature. Then now we have understood that you have, as a dependent on delta, with the isotropy value, you can really cross different transport regime. If you want, you can think of them of a phase transition, but it's not exactly correct, or at least people aren't still haven't argued on this. But basically here you see standard diffusion. Here you see ballistic for reasons that actually were understood already for a long time ago. But this special point, which is also correspond to S22 point, you see super diffusion. Okay, and this observation. Okay, let me just tell this. This observation captured a lot of attention, both by, so it was a numerical observation. It was a numerical observation, for example, that people have found by running a multi-scope state simulation. So, for example, this is the plot of this spin correlation at time x and plotted the function of x, but rescaled with t to a power 2/3, which because the dynamic exponent that we are witnessing here is 3/2. And you see that it has a perfect collapse, and it's also collapsed on a function that is known. I will tell you later what it is. But also there was a cold atom experiment on these. Basically, cold atoms, they can prepare arrays of atoms, and in Munich they can actually have basically have a spin microscope. They can really observe the spin at each lattice position. So they prepare like a domain wall of spin, like less spin, more magnetized, less magnetized, let it evolve. And you see that the magnetization transfer grows as it t to the 2/3, which is 1/z, the dynamic exponent, equal to 3/2. And okay, so this was a cool problem, got a lot of attention because somehow it's hard to find this kind of anomalous scalings, especially for model on the lattice. This is the comment that if you don't understand it, it's okay. But typically the lattice breaks a lot of structure, and typically you see diffusion for a quantum, for a classical quantum. So it was a surprising remark, and okay, and I'm going to tell you a bit how to understand this phase diagram. So, and in order to understand it, basically you have to understand that now what are the quasi-particles of this model. Okay, so basically now you have to imagine that your coarse grain description is made by these kind of little rods moving in the system, but the rods actually can be of different lengths, okay? Because there are different lengths on this system, and this because basically the simplest expectation you can think about like magnets. They can opt. So these are the magnets now become your single site rods of the length, I don't know, 1. But these magnets can make bound states, so they can move coherently through the system. Once they made a bound states, they never break it in the integrable. If the Hamiltonian is integrable, the bound state is stable. So it just became like a new type of particle, which are represented like this. Okay, just like now it looks like Star Wars, but it's just mean that you have like rods of different lengths and which interact among. And there is a peculiar effect on the way. Okay, I should have said that this exponent 3/2 actually was observed also in neutral scattering experiments, but I guess you heard the talks of John Moore about this. Okay. I forgot that actually I introduced it here. Okay, so let me tell you why people were so enthusiastic about this dynamical exponent 3/2. So the dynamic exponent 3/2 actually emerged in a universality class, which is not, which is a bit fancy, and it's called Kardal-Paris-Zhang universality class. Now, what is it? It's basically two equations, it's two partial differential equations. Either you want to state as the KTZ equation, which is an equation for the growth of a surface. You have a surface that grows by deposition, but also has some non-linearity, like this gradient of h square because it tells you that basically the surface should grow on the direction perpendicular to the slope, not just on the z direction. This introduced like a rotation in the growth rates, which actually at the first order is represented by this gradient of h square. H is the surface function. But by writing dxh equal q, actually you find another model which is dual, and it's the stochastic Berger equation. And now you see this is an hydrodynamic equation, because it's in a continuity equation, which is dtq equal dx something, where something is the current of q. And this current has a nonlinear term. It's proportional to q square, plus diffusion and noise. Now, in one dimensional, the nonlinearity and the noise plus nonlinearity is the deadly kill. Basically, you move always away from the Gaussian fixed point. You always go to this fixed point, which is KPZ point. That was the point of there was too many points. That was the point of the 1986 paper of Kardal-Paris and Zhang. Basically, the nonlinearity is always relevant in one dimensional. In two dimensional is intermediate. I forgot. It's not marginal. I don't know why intermediate is. And in two dimensional is not relevant. And basically, okay, in one dimensional there is this is such that in one dimensional there is a large universality class. As soon as you have a bit of linearity, you flow to this different dynamical fixed. And what is dynamical fixed point is characterized by dynamical exponent, which is not 2 as it is for diffusion, but is 3/2. But also that, for example, 2-point function are described at large time by a universal scaling function, which, for example, for the Gaussian universality class will be the Gaussian, but here it's a function that called LPTM, and it has a particular shape, and it's a bit different from a Gaussian. It has different tails. And also the fluctuation of the field, are not, again, not Gaussian, but are described by probability distribution that also emerged in random matrix theory. This is one of the most fascinating field of mathematics. Basically, there are distributions that come from the fluctuation of eigenvalues in random matrix theory that also enter to describe the fluctuation of the fields Q here. And the most relevant here is the so-called Weierstrass distribution. It's a distribution which has a Q-nan, because indeed this equation is not, as the time of time, is not invariant under changing h minus h, right? So if the surface is growing in one direction, it's not the same as going the other direction. So there is a clear sign of time as well. Same here. So all this distribution actually has Q, just because there is no time. There is a particular direction of time. Now, as I said, indeed, this equation appears, I don't know, in snow deposition, coffee beans, bacteria grow, and there is well, here, okay, the only thing is the surface, this is the surface, but this is the surface, this is H. But also it also emerged in the hydrodynamic of, in one dimensional hydrodynamics of non-integrable system, like, for example, anharmonic chains, Fermi-Pasta-Ulam. This was actually is much more a recent result. It was introduced by Herbert Spohn with this theory, nonlinear fluctuating going on. So the point is that typically people think of Cabrezzi equation as an equation for the growth of the surface, but there is also an entire work described by the stochastic Berger equation. Whenever you have an hydrodynamic with nonlinearity, typically this will be unstable under the additional nodes. And that's very important. Okay, so what is the key point here? This model is integrable, so it's already quite strange that the transport is purely diffusive, at least for delta larger than 1. As I told you, indeed, these models display purely diffusive transport when delta is larger than 1 for the spin. The spin is the only transport is only diffusive, while, for example, the energy is ballistic because the model is still integral. Why is that? But the reason is because there is an effect that is basically a screening. There is a screening or monetization of all these different type of quasi-particles. So how can we think these different species of quasi-particles? You can think that it's a bit bare, but it's correct. I mean, it is a square, it's different. So basically, now you see, this is, for example, the quasi-particle with spin 1/2. Or 1, this is the quasi-particle spin 3, this is 2, 4, okay, these are like bound states that they move together. You can associate a bare monetization to them, and it could be indeed S, like it's 1, 2, and so on. And there is a certain density of them at equilibrium. Say that I'm interested in a thermal state, there will be some density of this quasi-particle in a given thermal state. But the problem is that when they scatter, actually there is they have to conserve the number. Because, as I said, the integrable model, if I give you an initial amount of bound states, after the scattering, you have to find the same amount. So when they scatter, they have to follow a certain rule to not proliferate the number of bound states. So imagine that now I have this scattering with him. If he actually would stick to it, it would create a bound state of 4, which is not allowed. It has to remain a bound state of 1 and a bound state of 2. So if you now follow the scattering and also impose Z2 symmetry, you see that basically what has to happen is that when he's moving, hitting these bound states, and it enters the other one, it has to flip its time to conserve this the number of spins. And when it exits out, there has been a delay, a shift on the one is picked by position and is exit out. But the point is that indeed, it has a moment where its spin is effectively been flipped. Okay, so imagine now him moving in a soup of all these different quasi-particles. Basically, its spin on its net spin is 0. It's not anymore +1. Okay. Now the same happened to them by scattering with the larger one. So basically, the larger bound state screen the smallest bound state. Eventually, if you wait enough time and you look at certain scale, you will see that all this quasi-particle with more spin, basically 1 over the monetization of the system, are demagnetized, namely they are paramagnetic. If monetization goes to 0, they don't have the effective monetization, the direct monetization is 0. And only for the very large one, the one that do not interact with anyone, conserve some finite spin. They carry some spin. Okay, so basically only the largest quasi-particle carries spin in this model. But what are the largest quasi-particles? The largest quasi-particle, we can think them as semi-classical solids. So imagine that you have a very large modulation of your of your ferromagnetic state. Why is that? Basically, the way you construct quasi-particle in this system is that you start from a ferromagnet and you flip some spin. Okay, no? Exactly as I was showing you. You flip for a single magnet, you flip 1 spin. For a bound state 2, like you flip 2. Or imagine that you flip many of them. But these are like, you can think them as very, like, they're actually wave packets of your Glowstone modes. Because remember that you have like an SU2, for example, for the Heisenberg spin chain, you have like an SU2 spin, you have a SU2 symmetry. So you have this the classical semi-classical spin chain actually is described by what is called Landau-Lifshitz equation, which was spectrum actually is the spectrum of the long wavelength Goldstone modes in your system. For example, when you break from SU2 to U1. And these are basically, all these Goldstone are basically, you can make a wave packet of them, and they are stable. They are stable under evolution, because that's what actually what this equation shows you. This equation, the solution of this equation, or this dynamic, or these Hamiltonian actually are solitons, so stable wave packets of Goldstone modes. Why do we care about the fact that they're Goldstone? Because they are quadratic dispersively. So if they have a certain size W, we know that their momentum scale is 1 over W. They are quadratically dispersive, so the energy scale is 1 over W squared. But this means that the velocity also scale is 1 over W. So there is quite, if you want, like kind of a scaling variance in the size and the velocity. And this, we see it exactly from this large mode in the chain. That velocity.
Excuse me. Hi. A question from Zoom. Why are you calling them Goldstone modes? I mean, there is no long range order, is there?
No. But here it simply comes from the fact that the ferromagnetic state, like the vacuum of the quasi-particle that you choose to construct a quasi-particle breaks the global symmetry of the system. Okay, and it's like, for example, you have a ferromagnet as a vacuum. Okay,
but at any non-zero temperature, you don't.
Yes, that's a very good.
Actually, have a ferromagnet, right?
No, indeed, your observation is correct. When I say Goldstone, indeed, you're thinking of zero temperature excitation. While here we're thinking of a finite temperature excitation. And indeed, that's exactly the point, is the fact that it's integrability that basically allow you to construct wave packet of these modes that are actually also stable at finite temperature. But indeed, otherwise, I would have this excitation only at zero temperature. Exactly, that's exactly true.
Okay, thank you.
The point is that this excitation exists, they are in the spectrum. In principle, I would expect them to be only at low temperature, but they're also in the middle of the spectrum, thanks to the effective integrability of this, the integrability of this semi-classical description. Now, basically, what is the image that one can have in mind? Is that spin is transported by these very large clumps of particles, but because they're very large, you would expect that they don't move. They're extremely massive, so they should not contribute to the dynamics. But instead, at the non-abelian points, actually the velocity is not supposed to spread exactly because they are obtained by clumping together Goldstone modes. So the velocity is actually just 1 over the size. It's not exponentially decreasing as it is when you break the SU2. Now, they are very large, they move a little bit, but they are so large, they transport a lot of spin, so they give basically infinite fluctuations. Now, of course, this is very qualitative. You would have to do a calculation to do that. But okay, I will not go into the details since it's quite late. But the point is that the way to treat these horrible monsters is to introduce a little bit of external magnetic field in the system. This gives a cutoff to the largest of these quasi-particles can create, with giant magnets. And the largest one, it has to be 1 over h, namely 1 over the magnetization of the system. And basically you do a rescaling of S and theta in 1 over h, and you get basically an hydrodynamic for these giant quasi-particles. which, okay, you can show that fluctuation normalization around normalization can only be written in terms of the fluctuation of the giant quasi-particle, and the giant quasi-particle have another dynamic that can be completely characterized and obtainable from generalized dynamics. And basically what you find is that fluctuation normalization now are related to fluctuation of giant quasi-particle in a nonlinear way. So basically you get a first equation for DTM, which has a current, which is proportional to the fluctuation normalization times phi. This phi is basically some combination of these giant magnons. And okay, up to here, you don't know exactly what to do. You need an equation for phi also. The equation for phi.
All the energy computation, we are basically using the ferromagnet as your reference state. And if I really take the ground,
what energy calculation?
For example, how much energy is in the particular Cergy-Paris and things like that. You are comparing to the reference ferromagnetic state with all spin up, right?
Yes.
If I compare it with the actual ground state of the quantum system, which is not a
no, it has nothing to do. The ground state of the system will be a superposition of many of these excitations that I have constructed with by creating excitation on this vector. Yes, no question about that.
So what is the point of talking about this energy with some other vector that you have constructed?
The point of this is simply to say that there are some excitation in the spectrum that are there, which in principle I could neglect because I say, but what's the point? I mean, they're just a long wavelength mode. But actually they kick in, they're the most relevant one when we look at spin transport. And those are the ones responsible for this basically super diffusion, or the flow into this different universality class. This is the point. It's just that you would normally forget them, but they are there. And we need to use them. That is exactly the
point. Normally I think of quantum mechanics, I have a ground state, I have low-lying excitations. If I'm looking at some long-time dynamics, I should think of this the low-lying excitations and so on and so on.
Here we are at final temperature. We are final temperature. So we are looking at final temperature spin transport.
Are you looking at finite or infinite in some sense?
You can also do infinite. It doesn't matter, but it doesn't matter. Any final temperature will work. We are in 1 + 1 dimension, so I mean it's fine. The point is that this final temperature spin transport will involve some particle propagation. And the question is, what are the most relevant particles that you have? In principle, there are all of them, but the one that really give you this exponent z3/2 is these giant magnets. That are
normally they would be suppressed by the thermal factors.
Yes, but
they will be there. They will give you this, but they would normally be suppressed by the
I agree.
thermal factors.
But here they are not.
Because you are at infinite or very large temperature. I don't think of why those fluctuations are not, down by thermal factors.
No. Here they are not suppressed because of integrability. Because basically integrability makes them stable. It is exactly like integrability preserves the bound states of two.
How are you creating the first magnets?
They are in the spectrum. So imagine that you take infinite temperature.
A typical state in the middle of the spectrum,
yes.
Which has overlaps with all of them. This is exactly the same as saying that I'm at infinite.
Yes, but any final temperature will work.
Okay. No, now I'm fine.
Great. Okay, so and basically the point is that these giant magnets give you another dynamic that it's another dynamic for the magnetization and all the other giant magnets. And basically now you still have an infinite set of equations that you need to truncate. So you have one for magnetization, and you find that magnetization basically interact with all the other giant magnets in this form of phi. And now you say, okay, I need to write an equation for this phi. In principle, I would have to solve all the dynamics of these giant magnets, but now I can use some symmetry or some wishful thinking and say that basically I want to close these two equations. I want to close them so the fluctuation of phi, they have to be related to the fluctuation of m or the fluctuation of phi itself. And then I have to use the fact that m is magnetization, so it's spin flip odd. So this indeed is good because this is odd, so A has to be spin flip even. Okay, indeed it has to be invariant under STP transformation. So here it has to be the square normalization. And also phi is a current because M is parity even. So phi has to be parity odd is a current. So also here has to be the square. And these two reasons, these two basically symmetry reasons allow you to write a closed set of equations for magnetization and this extra mode phi that contains a lot of these giant phi. Then you proceed as typically in fluctuating hydrodynamics. You add noise and diffusion. Diffusion is there to enforce fluctuation dissipation, and you have two coupled Berger equations, which now you have to show that was universality class actually fall in the KPZ universality class. And this is very hard to do analytically. There's no really way. Interesting, it's a problem that Kardar already had attached, Kardar and Ertash had attached in 93. We didn't know about this, but we found out later. He was studying drift in polymers, and now drift in polymers can have different components. So he was writing equations for all these different components, and he was finding exactly the same set, the same two coupled Berger equations that we find. It's quite interesting that these two models are related. But basically, what you can do is to do numerics. And first, you impose that you impose fluctuation dissipation, namely you impose that Gaussian stationary distribution is Gaussian. This is something you have to impose, but Kardar already has shown by RG that this is a fixed point of dynamics. And then you do some numerics, and actually numerics shows you that there is an effective decoupling. At lifetime, these two modes decouple in two independent Berger equations, one with chirality plus and one with chirality minus. So the chirality is the sign of this square interaction. Basically tells you in which direction privilege this field to move. And manipulation becomes just the sum of these two chiralities. How do we say this numerically? Is because we compute the distribution of fluctuation on normalization, which is also scale invariant if you divide it by t to the 1/3. And this distribution for different lambda phi actually converges a lifetime to the same distribution that you get if lambda phi is equal 1, and lambda phi equal 1, and lambda n equal 1. You can see that basically it's exactly the point where these two equations completely separate into two independent modes. So what we have found is simply that this giant, you can reduce this giant quasi-particle. There are many of them, but you can take basically the two most important, the one that move a little bit left and the one that move a little bit on the right. And these two, you can show that their hydrodynamics is nonlinear. It has a square part. So it means that if you add the noise and dissipation, which of course comes from thermal fluctuation in the system, it will lead to two independent Berger equations. And what you physically see in the lab, magnetization, is the sum of these two modes. It's completely the sum of these two Berger modes, one going left and one going right, is completely symmetric. So it doesn't have any skewness, and this indeed it's what was observed experimentally. But still, it has KPZ fluctuation if you actually compute, for example, the two-point function. Two-point function is described by KPZ fluctuation, but also the two-point function, the other field phi, it has KPZ fluctuation, but the other field phi is not observable. It's like kind of a current of giant magnets that you cannot really observe experimentally. The only thing that you have access to is just the density, the total density of these two species of magnets, and that's the manipulation. Okay, so it's a quite involved derivation, but it's not valid. It's not that it's only valid for Heisenberg SU2, but we also have shown that it's valid for any system which has non-abelian symmetry and also integrability. So you need non-abelian symmetry and integrability to keep this Goldstone mode stack to be in the spectrum also finite temperature, exactly. But the KPZ emerged from exactly this nonlinear, this partial differential equation that you get when you take the hydrodynamic of this joint quasi-particle that only exists in the spectrum at this particular non-abelian point. But okay, there are a lot of questions like this. Of course, I made a lot of simplification because I have only assumed that there are two possible velocities for these giant manions, a bit left, a bit right, but in principle, there are many more. So it's a bit hard to understand actually how you decouple at different velocity. Also, the one we have absolutely no understanding of this set of coupled equation. We could only do numerics. It would be great to do maybe a better RG to show this decoupling last time. Okay, and with this, I'm done. Thank you.
Let me ask the Zoom audience if there are any questions. Okay, if not, any questions from the other?
Sorry, I didn't know. I had thought probably mistakenly that in systems with integrable states, you have an infinite number of conserved charges. The appropriate hydrodynamic description would not follow just 1 or 2 charges, but an infinite number.
Exactly, that's the rho theta.
Rho theta is.
Yes. Voila. That's the density of charges at this position in space and time. Thank you.
So I missed the point. Where did the SU2 symmetry go to the differential? Where is the least?
So basically, you can think it like this. You want to have an equation for magnetization, okay? An hydrodynamic equation for magnetization. No, that's not the one. Yes. So you can think that this will be very crude, but it won't. So you ask yourself, what's the current of magnetization? Can there be m squared? No, because it would be simply even. So it cannot be m squared. Can it be m? Yes, in principle, yes. But this would give a final velocity, and we know that the final velocity is 0. So it cannot be anything with m cubed. So it can be m times another field, phi. And this phi, by the way, has to be parity odd because it's the current. Yeah, by the way, this also cannot be true. And now you say, I write what's the current of phi? If I assume that it only depends on m on phi, it cannot be m because it's odd. It cannot be phi because it has to be parity odd. So it has to be either m squared or phi. And of course, okay, I neglect higher powers. I only want the leading term.
Any others? If not, let's finally go again.